So we have here a sample problem. A group pile in clay is shown in our figure. So we have here the figure for our sample problem. Determine the consolidation settlement of the group pile. All clays are normally consolidated. So the length of the pile are 15 meters each. The stress distribution starts at a depth of 10 meters below the top of the pile. So the consolidation starts at 10 meters below the top of the pile. So this is where the consolidation starts. And we are given with our Q sub G, which has the load acting on the top of the pile, which is 2000 kilonewton. We're going to, for our calculation, let us calculate first the settlement at layer 1. So this is normally consolidated clay. So this is the formula that we will be using. So first, you have, for layer 1, you have to get the value first for our increase on the vertical stress, which is given by Q sub G all over as L sub G plus Z sub 1 times B sub G plus Z sub 1. So therefore, if we try to substitute the given values, that is equivalent now to 51.6 kilonewton per meter squared. And our vertical stress for layer 1, so the effective vertical stress, actually this is, we're going to have here for our layer, for each layer, multiply the height on that layer multiplied to the unit weight. So for this layer, we're going to have the first layer. This is the first layer. We're going to compute for the vertical stress on this point. So the vertical stress here would be equivalent to this height times the unit weight, which is, this is 3.5 plus 9. So that gives us 12.5 times the saturated unit weight. So subtract this by the unit weight of the water, so 18 minus 9.81, then plus this height, which is 2 times the unit weight, which is 16.2. So that is now the vertical stress, which is 134.8 kilonewton per meter square. Of course, this concept was learned also in solid mechanics. So therefore, if we try to substitute now the values of these parameters that we have computed, we have now equivalent value for the settlement at layer 1, which has 162.4 mm. Now we move on to layer 2. So we're going to have this equation. So similarly, we're going to compute for the vertical stress at layer 2. So if we're going to compute the vertical stress at layer 2, this is layer 2. So this is, the vertical stress would be half of this is 2 times the unit weight, which is 18.9 minus 9.81, since this is saturated, then plus this height, which is 16 times 18 minus 9.81, then plus 2 times 16.2. So our vertical stress here will be equivalent to 181.62 kilonewton per meter squared. And our change in the vertical stress using the formula that we have a while ago will be equivalent to Q sub G all over our L sub G plus Z sub 2 times B sub G plus Z sub 2. So this 9 actually is equivalent to this one. 9 will be from this portion. So that is equivalent to, this is half of this is 2 plus this one plus 7, so that is 9. Because our Z starts from this point going down. So we have here 14.52 kilonewton per meter squared. And if you try to substitute this given value, we get now for layer 2, the settlement is 15.7 mm. Then the settlement of layer 3, similarly, we have to get the value for our vertical stress. So at layer 3, so this is our layer 3. So from this point, so get the vertical stress. Half of this is 1. So 1 towards this surface, that is 1 times the unit weight, 9 times, this is 19 saturated, so minus 9.81, so that would be vertical stress will start here, so that is vertical stress equal to 1 times 19 minus 9.81, then plus from this layer towards that layer, from this point towards this point, so that is 4 times 18.9 minus 9.81, then from this point towards this point is equivalent to 16 times 18, then plus 2 times 16.2. All of those that are saturated should be subtracted by the unit weight of the water. So if you try to sum up that one, it gives us 208.99 kilonewton per meter squared. And the change in the vertical stress will be Q sub G 2000 over L sub G plus 12 times B sub G plus 12. This 12 is actually from this point, this is 7 plus 4, 11 plus 1 towards this point, so that is plus 1, so that is 12. So we get now 9.2 kilonewton per meter squared. And if you try to substitute this value, we get the settlement at layer 3, which is 5.4 mm. So therefore, our total settlement will be equal to settlement at layer 1, which is equivalent to 162.4, then plus the settlement of layer 2, 15.7, settlement of layer 3, which is 5.4, we get 183.5 millimeters. Okay, for piles in rock, for point-bearing pile resting on rock, the most building code specify the Q sub G is equal to the summation of Q sub U, and provided that the minimum center-to-center spacing of the pile is D plus 300 mm. So for each pile and piles with square cross-section, the magnitude of D is equal to the diagonal dimension of the cross-section of the pile. So that ends our discussion for pile foundation. So basically, pile foundation is a deep foundation that is used for weak type soil for safety, structural safety purposes. So this is basically used for buildings that are high-rise building, and you have a weak layer of soil, so we cannot resolve that through a shallow foundation. So we're going to use a pile foundation to have a safety and stable structure that will be constructed on that ground surface. Thank you.